for the design, we need to consider this. We are going to consider 3 cases, from simple to complex. The first case, we don't consider calibration. The second case, we allow individual calibration because we have several load cells. And finally, it's automatic calibration. It's more advanced. If you look at, we have 4 Keystone bridges. Then for each Keystone bridge, see 1, 2, 3, 4. Assume we apply the same force to each bridge. So they got the same force input, 100, 100, 100, 100. This is ideal case. But in reality, different bridges will have different force. But we start from the simple one. Then the maximum is 100, the load capacity for each load cell. So now the 4 load cells, Keystone bridge is maximum capacity. Then these are all, and this is R. See, we have this is compensation resistance. RS, 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 and we have RO, the initial resistance. So for initial resistance 2.2 k ohm, the compensation resistance 464 ohm. So for each case, we need to calculate the resistance change due to the load. So we have 4 RR1. We got 1, 2, 3, 4. So these are used to calculate the resistance change due to the load. Okay. So now everyone need to create this circuit. Then come back here, put your file in a USB file. Then I will assign randomly to come here to present your circuit. What's your name? Wenjin. Kunjin. How much time? ASC file. So you need to, okay, wait a second. Maybe install the piece file. Okay, so those cells, 1, 2, 3, 4. Now, their voltage output for each load cell, because they got the same force, so their output should be matched. And their impedance, assume every resistors, there's no tolerance, so their impedance is also well matched. So now for this one, we have the 5 volt, the positive rail, 5 volt. The negative rail is minus 5 volt. The dual rail power excitation voltage. Okay, now everything is perfect, but in reality, the world is not perfect. We have imperfections in the circuit. Then, for any differential amplifier to work, because the input impedance should be infinite, but here the input impedance is not infinite. So probably we need a buffer. We need to put an OP in front of the inverting input and non-inverting input to provide an infinite impedance, infinite input impedance for the Wheatstone's bridge. So that's why we need instrumentation amplifiers. But we don't want to use a lot of instrumentation amplifiers for each bridge. We want to decrease the use of the expensive instrumentation amplifiers. So we may try to use summation or subtraction of all the Wheatstone bridges, combine them into, say, one input buffer amplifier and the other input amplifier. Okay, so yeah, what we will do. Okay, this is what we will do. We use one OP to take the positive output of the 4 Wheatstone bridges. We use another OP to take the negative outputs of the 4 Wheatstone bridges. Then after that, we use another OP. So this is the summation of the 4 positive output. This is the summation from the 4 negative inputs. Then we put them into this differential amplifier to get the differential output. And here, the excitation voltage plus, see, EXE plus, positive supply. This is negative supply, negative supply. We add one coupling capacitor to remove the AC noise from the power supply. Okay, so now you need to create this, and what I like to tell you is that now the gain of this OP, so this is 10K, this is 12.5K, so the gain is 5 divided by 4. 5 divided by 4. The ratio is the gain for each one. But we have 1, 2, 3, 4. They are added together. So actually, 5 divided by 4 times 4 is 5. So this is the gain 5 for the first stage. In the second stage, 50K, 10K, another gain 5. So the total gain is 25 to get to the output. Then for the load cell, okay, you buy the load cell, the company will tell you the spec for your load cell is 20 millivolts per volt excitation voltage. So now in the excitation voltage, remember this is double rail. We have 5 volt minus volt. So the total excitation voltage is 10 volt. So 10 volt is the excitation voltage. And the spec for each load cell is 20 millivolt per excitation voltage. Okay, so the output of the Wheatstone bridge 10 times this number is 10 times this number, 20 millivolt. So 0.02 volt times 10 is 0.2 volt. And this is again, so 0.2 times 25 equals 5. So in the perfect world, the output is 5 volt, here, 5. But if you run the simulation, the result is not 5, it's 4.5. Okay, now this is the LT spice you created, but now I want you to, based on this one, so add all this to the previous Wheatstone bridge. Okay. So, how much time do you need to add this to your previous LT spice? You don't know? Okay. Adam, Ami, how much time do you need? 30 minutes. Okay, please come back here. 2:30. Okay? To combine this, see the output according to the PPT. So the total gain is 25, and the output from the Wheatstone bridge 0.2. So 0.2 times 25, 0.2 amplified by this two-stage amplifier. The output should be 5 volt. But if we see, you run the simulation, the result is around 4.5. 4.95. Why? It should be 4.5. So, can you see what's wrong with huge circuit? Huh? Okay. Hi, Ami, could you show me your result? Let's see. You should click on, maybe click on this one? Yeah. Yeah, click on this one. Okay, result should be 4.5. So, Ami result is correct. So, can you explain what's the difference between your circuit and his circuit? Can you put these two?
Yep. We have a resistor here and a U.
Okay, yeah, he didn't put because this is the. Okay, so this is the differential amplifier. So the non-inverting input and inverting input, 10K, 50K, we should have 10K also, 50K here. So they have the same amplification ratio. Okay, so this is the problem here. So why we have this 4.5 volt result? It should be 5 volt result. So the reason is about the input impedance, the buffering. Because the input impedance should be infinite. For this OP, the input impedance for this OP is infinite. But in reality, the signal goes this way, then goes this way to output. So the signal didn't see this one. Instead, the signal goes this way. So it sees 10K and 12.5K. So this is the problem. So we can do the calculation. So in order to do this calculation, we need to know this is the Wheatstone bridge. We need to know the output resistance. We have calculated this Wheatstone bridge output resistance already in the previous class, but see, the signal comes from, for number one, we have positive, negative from bridge 1. So half the circuit goes to this end, half goes to this end, and in series with 10K, 10K. So let's look at this. The output resistance, this is Wheatstone bridge. So we want to test the output resistance. We put Vx, Ix, and Vx divided by Ix is the output resistance. So, but just suppose this branch and this branch we have resistance this one. This branch we have resistance this one. So we can say the output resistance equal to this one plus this one. So for this positive branch, it should be half of the output resistance. Okay. So the output resistance, you can use this equation to calculate 2.19 kΩ. Then this is output. So see, this is 0.2, and we have 4 Wheatstone bridge. Then for each one, if you look at this stage 1, so output resistance, and this one is the 10K. So the amplification, the gain for stage 1 is this value divided by this one, this branch. So this one RF here, and divided by this is RI is 10K, so 10K is here, and this one is the output resistance of the Wheatstone bridge divided by 2. So this is stage 1 gain, and stage 2 gain is this value divided by this value. This is gain for stage 2. So this one, if Ri is much larger than this one, then we can ignore this one. If input resistance is infinite, then this one we can ignore, so we are happy. But unfortunately, the input resistance, this one, only 10K. So that's the problem. So you can do the calculation. The result, hand calculation, result is 4.5 volt. Exactly the same as this one. Okay, so everyone, get the paper and your hand. Follow this calculation by hand and get the result. Okay, start, please. If you don't understand, please ask. So those 3 electrical engineering students, you can ask it. Are you understand? Do you understand? Kaiser, do you understand? If you are confused, you can discuss with them. So do the hand calculation. Don't just copy the result. Don't just copy. Don't be a robot. Do the calculation. Plug in the numbers. Get the result by yourself to get the feeling of this calculation. If you just copy it, you are wasting your time and you are wasting my time. But if you do the calculation by yourself, plug in the numbers, use the calculator to get the result, you will learn more. So later I will assign one student to come to explain this whole process, the meaning of each variable. You don't need to derive this one. You just plug in the numbers to do the calculation. You don't need to derive this one. You put in the numbers to get the result. But I will ask one student to explain to me the meaning of each variable. And also to explain how to derive this one. So please ask the other students if you have a little bit confusion about this. Make yourself clear about this simple OP circuits. This is good because for mechanical engineer, you are going to use this a lot to measure your result. So mechanical engineer, you also need to learn this for experiments and measurements. So everyone, we will continue our class around 3:10. So you have 25 minutes. You can, if you need to go to the restroom, or we will start the class 3 o'clock, 10 minutes after 3 o'clock.
This one is at minus at what? F? Like this? Really?
Yeah.
Like this?
To modify the circuits to get the 5 volt output. Okay, that's one way to increase the output voltage to this number. They remove 2 OP, they just use 1 OP. And they increase it to 600K, 100K. So in the past they used 10K, but now they use 100. So it will improve. So this is 600K, 100K. So the gain is 6 for this OP. But remember, we have 4. 1, 2, 3, 4. So 6 times 4, 24. Now this is the amplification, 24 for this circuit. So 24 and 10 is the excitation. rail to rail. And 0.02 is the Keystone bridge because 0.02 volt per excitation volt. Okay, so this is the voltage from the Keystone bridge. This is the application. So result should be 4.8 volt. Okay, 4.7. Close. So everyone, please go back to now use this one OP to replace your circuit. Your previous circuit has 3 OP. Now we have 1 OP. And carry out this and run the simulation. Okay. So wait a second. Yun, what was your name? Yunjun. So how much time do you need? $20 minutes. Okay, 450. Although in this circuit, we increase the resistance to 600K, 100K. It's large. So the result should be 4.8 volt. 4.8 volt. But it's not. Still, 4.8 and 4.75. They are 50 microvolts difference. So, although it increased the resistance, still we are not happy with it. Because although the buffering is improved by increasing the resistance, but still it's not good enough. Also, there's one big problem. Resistor is noise. Even you increase to 600K, the noise, thermal noise, created by the resistors will be large. Remember, the noise density is 4 kTr. The resistor noise is 4 times Boltzmann constant times temperature times resistance. So large resistance, it will increase noise, voltage noise due to the resistors. So also for each OP we have input bias current. So input bias current goes through the resistance. It's going to create input offset voltage. Input offset voltage will have the common mode output. So a lot of things we wouldn't suggest to increase the value of the resistance. So what we will do, buffer, we need to use buffer OP. So one buffer OP, another buffer OP is important. But see, this is the old one. Due to the feedback, you won't see this high input resistance. So we need to make some difference, make some improvements. This is the improvement we are going to do. See, for this circuit. Now let's know feed-forward pace. Feed-forward pace from input go to this feedback, go there. So this looks like a voltage follower. Voltage follower. Signal goes here, and the signal sees a very large input impedance. So now we have a very large input impedance in this case. So remember, voltage follower means this is V input, see V input here. Because there's no current, So you can think there's no current here. So this voltage, there's no current, so the voltage here the same as this voltage. So VI equal to V plus. V plus equal to V minus. And this one goes here. So V output equal to V minus. V minus equal to V plus. V plus equal to VI. So which means VI equal to VO. So this is voltage follower. Output follows input. Voltage follower. Awesome, do you understand? Okay, we use voltage follower for buffer operation. Okay, we got an equation here. V sig 1 here. This is VO. VO equal to V minus. V minus equal to V plus. So this point is VO. So V sig 1 minus VO divided by 10K. And the current here, this one. The current here, this one. The current here, this one. And the current here, this one. So use Kirchhoff current law. I1 plus I2 plus I3 plus I4 equal to I out. But I out goes to this one. There's no current here, so it means I1 plus I2 plus I3 plus I4 equal 0. So you just arrange this equation, you can get the result. VO equal to V sig 1 plus V sig 2 plus V sig 3 plus V sig 4 divided by 4. So this circuit is a voltage averagers, AVER, AGER, because this circuit takes average of this input value. The same, you can, this one is the voltage averager for sig minus 1, sig minus 2, sig minus 3, sig minus 4. So you take average input to this one. And so sig plus this one. And sig minus this one. Go through this differential amplifier. So now the gain is 25 plus 0.5K, this is 1.02K. So this is ratio, gain is 25.5K, 1.02K. So the gain for these two is 25. And the voltage follower, the gain is 1. Okay, so that's what we do. So the differential amplifier gain is 25. So okay, so this is the new circuit we will use. So now for this new circuit, we have 4 Wheatstone bridges, but each bridge experiences different force. So bridge 1, 10, bridge 2, 30, bridge 3, 70, bridge 4, 90. So this is the reality. Different bridge experience different force. And the maximum force for each bridge, the capacity is 100. And again, 20 millivolt per 1 excitation volt. And this is RS compensation resistor. This is initial resistance, 2.2K. So we can calculate the mains resistance change using these 4 equations. Then you can put them into this circuit to test if your circuit can work. So Wheatstone bridge 1, 2, 3, 4. You run the analysis. result is good. Now it's almost 2.5. We are happy. We got the right circuit to work. Okay, so we run out of time today. So next Tuesday in the class, please bring your circuit inside your USB and come to the class. I will assign one student to show me, to run the circuit and show this result. Okay? Thank you for your attendance. Look forward to meeting you next week. Bye bye, everyone.